Alright everyone, I'm going to go back over the notes for those of you that missed it or just need a re-explanation. But I had y'all all go and count some M&Ms, and it turns out that y'all found 70 brown, 85 yellow, 70 red, 116 orange, 83 green, and 124 blue M&Ms in your packages for a total of 548 M&Ms. Now, Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&Ms milk chocolate candies. On average, M&Ms milk chocolate candies will contain 13% of browns and reds. So if we found 13% out of the 548 would be our expected, we would expect to see 71.24 for both brown and red. And we found 70 and 70, so that's not too far off. Alright, we would expect to see 14% yellow, so that would put us at 76.72. We would expect to see 16% green, so 16% of 584 is 87.63. And we would expect to see 20% oranges, which would put us at 109.6, and 24% blue, which would be 131.52. This should add up to be the 548, just like before, if we did our percentages correct. Now, here's the deal. In the past, you could test out whether or not this would be an expected proportion by using a 1 proportion z-test, but you don't really want to have to do it 6 different times. And so that's where we use a chi, which is C-H-I, it's a Greek letter, square test, or a statistic, to measure these things, okay? And so when we took the difference, we had 0.021, by difference I mean the observed minus the expected squared divided by the expected. So we're using this formula here. So it would be 70 minus 71.24 squared, divided by 71.24. So we had 0.021 here, 0.89 here, 0.021 here, 0.374 here, 0.25, 0.43, and we add these up and we have 1.986. Alright, and so the chi-squared statistic, or chi-squared, it measures how far the observed counts are from the expected counts. The formula is the chi-squared is equal to the summation of the observed minus the expected squared divided by the expected. And so what we did here, this is sigma, this is an uppercase sigma, our lowercase sigma is like here, and this is for standard deviation. This is a reminder for you. So this is an uppercase sigma, and it's used for summation, and so that's when you find each one of these observed minus expected squares divided by expected, and then you add it up. That is a summation. Alright, so larger values of chi-squared are stronger evidence against the null. And you'll see, like here, this was a difference of almost 8, a little over 8, and so we had a larger number here, and so that shows that it's farther apart. Here, the distance is almost 8. Here, it's 7.5 or so, and it's lower because it started off as a larger number, and so whatnot. So, and that's because they say that observed counts are far from what we would expect if the null is true. Small values of chi-squared suggest that the data is consistent with the null hypothesis. So to calculate your chi-squared, okay, it looks like a giant cursive X. It's just a capitalized X here. You do R observed minus R expected. So we're using these numbers back up here. You're squaring that, and then you divide it by the expected, and then you would add it to the next one, which the next one would be 85 minus 76. And then you would divide it by the 76.72, and you'd keep doing that all the way through our blue. So that would be the 124 minus the 131.52 squared divided by 131.52. And whenever you add up each one of these fractions, we'll get what we got here, the 1.986. All right. So we could not perform a significant test taking all of the colors into consideration at once. You could do it one at a time, but then it still doesn't look and see how we could compare those to getting a result like that. So we need a new kind of significant test called the chi-squared goodness of fit. So we're looking to see how good does this fit. All right. When the expected counts are all at least 5, so that is our condition, is they all need to be at least 5. So if you only expected to see 1% of something happen 1% of the time, you'd need a sample of at least 500, so that 1% of 500 would be 5, and you can have a smaller sample than that. So instead of having like the 10% condition, we're looking at that. So the chi-squared distributions are a family of distributions that take only positive values, and that's because we're squaring, and are skewed to the right. And that's because when it's all positive, it's like when we had our geometric distributions, they were skewed to the right as well. Okay. And a particular chi-squared distribution is specified by giving its degrees of freedom. The chi-squared goodness of fit test uses the chi-squared distribution with degrees of freedom equal to the number of categories. So like in our M&Ms, there are 6 different colors, so 6 categories minus 1, so the degrees of freedom for that one would be 5. And you can see that it becomes more normal-ish the more categories we have. All right, the mean of a particular chi-squared distribution is equal to its degrees of freedom. And degrees of freedom greater than 2, the mode is the peak of the chi-squared density curve at degrees of freedom minus 2. So this had degrees of freedom of 4. I guess this is a poor drawing. But like here, you can see the degrees of freedom is equal to 8. So the mode would be at 6, which would be our peak. This one seems off. Looks like this is really, minus 2. Yeah, so 4 minus 2 is 2, so that's where the peak is. All right, and this one does not have a peak because 1 minus 2 is negative 1, which would not be on this graph. So when, let's say you had categories equal to 9 different categories, the degrees of freedom would be equal to 8, because 9 minus 1 is equal to 8. And the chi-squared distribution has a mean of the degrees of freedom, which is 8, and a mode of 6, because it's 8 minus 2. Okay? To get p-values from a chi distribution, we can use table C or technology, which is what we are going to use in here. All right, I'm going to pause it, and I'll come back in the next video.